Let's look at a couple problems taking into account Bernoulli's equation. Here's the first problem. What is the maximum height to which water could be squirted with a hose whose velocity is 1.96 meters per second and whose area, cross-sectional area, is 2.54 times 10 to the minus 4 meters squared? Okie doke. Let's take a look at how we would go about doing this. We know the fundamental equation is Bernoulli's equation, which states that P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. Now there are certain assumptions we have to make. First of all, that in both situations the pressure is going to be equal to each other and is equal to 1 atmosphere. But since the pressure is equal to each other, then we can take those out of the equation. This, by the way, is 1.01 times 10 to the 5th pascals, in case you were wondering. Secondly, we have to say that V2 is equal to 0. V1 is what we're given, 1.96 meters per second. And H1 is equal to 0. And H2 is what we want to know. Now, since H1 is 0, that cancels this out. And since V2 is 0, that cancels this out. And so you end up with 1/2 rho V1 squared is equal to rho GH2. The rows cancel each other out, and you've got 1/2 V1 squared is equal to GH2. And so that means that H2 is going to equal V1 divided by, V1 squared divided by 2G, which is equal to 1.96 squared divided by 2 divided by 9.8. And if you do the calculation here, you get 0.196 meters. So not real high. Now the second part of this problem says you put a nozzle on this hose and it has a cross-sectional area equal to 1.96 times 10 to the minus 5 meters squared. So the question now is what is the new height? Well, what this new cross-sectional area does is it changes the value for V. Everything else remains the same. And so A1, two ways you can calculate this. A1 V1 is equal to A2 V2. And because we don't know A1, we don't want to have to calculate that, we can also say that Q, which we know, is equal to A times V. And so 1.96 times 2.54 times 10 to the minus 4 meters squared. So this is if you take this velocity and this area from the original problem, you can calculate Q from the original problem, and the Q here is 4.98 times 10 to the minus 4 meters cubed per second. Then you use this flow and this equation again to calculate a new velocity, and it's going to be 4.98 times 10 to the minus 4, now divided by 1.96 times 10 to the minus 5. That gives you a new velocity of 25.4 meters per second. Then we take this velocity and insert it here. So the new height is going to equal 25.4 squared divided by 2 times 9.8. And that's going to equal 32.9 meters. So here's two problems using Bernoulli's equation. The first one is fairly straightforward, and you have to make a few assumptions here. And then the second one. Now let's move on to another equation called Torricelli's theorem, or Torricelli's theorem. And Torricelli's theorem is related to this situation here. You have one situation that has a P1 and a V1 at a certain height, and a second situation that has P2 and V2 at a second height. And Torricelli's theorem relates these two situations. So water will gush out of the base of a dam made in this way. In the absence of significant resistance, that is, if you assume that in this area here there is not significant resistance, water will flow from a reservoir at the same speed it would have had if it fell the distance h without friction. So the speed here is the same as it would have been if it fell and when it reaches, say, as a waterfall over the top. And so this is what Torricelli's theorem says, is that this velocity here is going to be the same as the velocity if it fell over the top and reaches the same point. And this is an expression of that. V1 squared, that is this velocity here squared, which in this case would be 0, plus 2 times gravity times the height difference is equal to the velocity squared of down at this point down here. Now this might look a little familiar if you remember your mechanics problems, and there is obviously a relationship there. Now what happens, or what this shows, is if you have a hose that has to go up a certain number of feet, then obviously the velocity at this point is going to be far less than if it was squirting at this point. So pressure in the nozzle of the fire hose is less at the ground level. The water going uphill, the speed has to increase at the nozzle. In spite of its lower pressure, the water exerts a large force on anything it strikes by virtue of its kinetic energy. The pressure of the water stream becomes equal to atmospheric pressure once it emerges from the air. Now, let's move on to the concept of viscosity. Now, from now on, we'll actually be talking about concepts, but we will not be working any more problems. Here we have smoke rising, and it rises smoothly initially, but the farther it goes, the more it gets disrupted. The smooth flow in this part is called laminar flow, and the more rough flow up here is called turbulent flow. You notice that it rises rapidly during its laminar part if you watch a cigarette smoke, but then once it becomes turbulent, there's more resistance and it slows down. Viscosity is the friction in a fluid in terms of the friction between layers of fluid, and I'll explain to you what I mean by layers of fluid in just a second. So anytime fluid flows, here for example, it flows in layers, and you can use various thicknesses of layers in a situation like this. Now A is a laminar flow situation without mixing, and the viscosity drag between layers is less, but what happens is you have here friction based on its contact with the bottom, and the farther up it goes, the less that this friction has, and the faster the flow is. Now B, on the other hand, there's an obstruction, and the obstruction breaks apart these laminar flow layers, and this causes turbulence. And the turbulent mixing that occurs causes more interaction, heating, and resistance to flow, and this becomes very chaotic in this area. So turbulent flow is a flow type where the layers mix, whereas laminar flow is a flow type where the layers don't mix. Now here's a way of looking at this in terms of flow and viscosity and velocity. At the bottom, the first layer, the bottom of the first layer, the velocity of the fluid at the bottom is 0. And as it goes up, it flows faster and faster until it reaches the velocity v. So this graphically shows that in laminar flow, each plate has an area A. The bottom plate is fixed because of its contact here, but as you go up, there's more motion, and the top plate is pushed to the right, but it has a drag on it. It's pushed by a force, but it has a drag on it. And this force that it's pushed by, it drags these fluids with it. And so you have increased flow here and decreased flow here. Laminar flow, as I said, is a situation where the layers do not mix. So if you have no viscosity, such as part A here, there'll be no resistance, and the speed of the fluid will be the equal throughout this tube. Obviously that's a arbitrary situation, because what truly happens is shown in B. The two layers that are closest to the sides flow the slowest, and they increase in speed until in the middle is the fastest plate or the fastest layer of fluid flow. It's a maximum in the center. And this occurs with any viscous material. The Bunsen burner, if you look at the flame of the Bunsen burner, it shows you this very same situation. Now this one you can't really see very well, except you can see the fact that outside is the slowest, and then the more centered to the flame, the faster it goes. And then this shows it even better. The central aspect of the flame is when flow is laminar in a large part of a blood vessel, but turbulent in parts that are narrowed by plaque. Now what that means is that if you have, this is a situation of a normal blood vessel here, and you have mostly laminar flow. But if you have a narrowing, like here, then the velocity increases and you have turbulent flow. Now this transition causing this chaos is what causes the noise that can be heard when you hear a heart murmur. That's the noise across a valve. Or what's called a bruit, which is a noise that is created inside a blood vessel. And it's created by this turbulent flow that occurs with the narrowing. There are three forces that act on an object that falls through a viscous fluid. The weight of the object, what's called viscous drag, and the buoyant force. You remember the buoyant force. So here we have an object that's falling through a viscous fluid. There's the viscous drag acting on it, called F sub V. That's the friction of the fluid that passes around the object as it falls. The buoyant force, which is the weight of the fluid that's displaced by this object, and the fact that the forces down here are greater than the forces above the object, and then those two act against the weight of the object. And here's the free body diagram that shows that those three forces acting together. Now the second concept that we want to look at is the concept of diffusion. And diffusion is the passive spread or movement of molecules from areas of high concentration to areas of low concentration. Diffusion proceeds from this area of high concentration to this area of low concentration. Now you can calculate, let's just say that this is delta X. This volume is delta X times A, This volume is delta X times A, and you can calculate a concentration 1 here and here. And the natural progression caused by diffusion is for this to decrease and this to increase. Diffusion is the movement of substance due to their random thermal motion. Osmosis is the passage of molecules across a membrane. So what you have is a semi-permeable membrane that will not allow these larger molecules to cross, but does allow smaller molecules to cross. A semi-permeable membrane with small pores that only allows these smaller molecules to pass. And so what will happen is the molecules will pass in an attempt to equalize the concentrations of the larger molecules. Certain molecules dissolve in this membrane and diffuse across it. That's what's shown here. So osmosis is the transport of water, the fluid that these things are sitting in, across a semi-permeable membrane. Obviously it's permeable to the water, from a region of high concentration to a region of low concentration. And the osmotic pressure is the force or the natural tendency for the water to dilute the higher concentration, and this is shown in this next slide. So here you have a semi-permeable membrane, and you have water, which is shown as small blue dots, and sugar, which is shown as red dots. The sugar cannot pass, the water can. So what happens is water passes across from left to right until the sugar concentration on both sides is the same. Now the back pressure here is the height times the density times G, and that represents osmotic pressure. So two sugar water solutions in different concentrations are separated by a semi-permeable membrane. The water can pass, but the sugar cannot. Osmosis will cause a passage from left to right, since the water has to dilute this sugar here. The fluid level will rise until this back pressure is equal to the relative osmotic pressure, and the net transfer of water is equal to 0. The back pressure which stops the osmotic process if one solution is pure water, that is, if you had pure water on one side, at some point it would stop because this pressure would counterbalance the desire for it to come across.